Good morning. There are a couple of details I wanted to discuss this morning while they were still fresh in my mind. One of these is the covariant and contravariant transformation of the differential of a vector field, and the other is the expression of a 2 by 2 tensor, 2 by 2 by 2 tensor in matrix notation. You may recall that Dr. Physics A discussed contravariant and covariant transformation of a tensor. Then I made an entire 18-minute video now titled Bewildered by Covariant and Contravariant, just saying that this distinction didn't make any sense to me. I think maybe if I start with a simpler example and move forward, I might be able to distill the essence of the point I missed. I would think one step simpler is the covariant and contravariant transformation of a vector. And 2 steps simpler would be the covariant and contravariant transformations of a scalar. Okay, let me see if this example takes us anywhere. I'll say x is measured in yards and y is measured in feet. So if I give you, so y is going to be equal to 3x. And dy dx equals 3. But now we've got this function, f of x, and we want to see what is df dx and also what is df dy. Df dy. Well, df dx is quite easily done. It's just 2x. But df dy is equal to del f del x dx dy, which is going to be 2x times del x del y would be 1/3, which would be 2/3 x, and since x is equal to, or y is equal to 3x, so this is 2/3 times x, or y over 3, or 2/9 x. Or rather, y. So let's summarize that using a little bit of extra notation. Dy is equal to del y del x times dx, which would be 3 dx. But then come down here, and we've got df dy is equal to del x del y times del f del x, which was 1/3 times 2x. Now that still hadn't been converted over into the y units at that time. When it's actually completed, it comes out to be 1/3 times x is 1/3 y, so it'll be 1/3 times 1/3 times 2y. But you basically get the general sense of contravariance here and covariance here. The contravariance comes from the conversion of a differential path element, while the covariance comes from the conversion of the differential of a function. Now I can look at the forms of these equations and see a bit more what's going on. Notice that you've got these x variables over here. If I divided the left-hand side by this combination, I would have y variables over x variables equals y variables over x variables. So if I have y's over x's equals y's over x's, I think that might be the essence of what contravariance is. And here in the covariant expression, we have y's. If you divide by the x's, you get y's over x's equal to x's over y's. And that might be the essence of what covariance is. Which the forms of these equations you use is probably in large part a matter of context. If you are trying to transform a tensor made up entirely of differential path elements, I'm guessing, you would probably use the contravariant form. While if you are transforming a tensor made up of the differentials of a vector field, you would probably use the covariant form. So you can see now why I asked this question yesterday. You don't discuss the transformation of a vector field except for the path element itself. Am I stumbling upon the rationale for distinguishing between contravariant and covariant? Is the difference between upstairs indices and downstairs indices the same as the difference between differential path elements and differentials of vector fields? At the time, I said, no, I guess not, and I referenced time 3336, you show a transformation of a vector field that suggests that it is exactly the same as the differential path element. So let's go to 3336 and show that part. Let's go to that section of the video, and you can see what he's doing here is using equation 1 as some kind of reminder of what to write in this equation. Now this turns out that it is a contravariant form because this is v sub y and this is v sub x. If you divide v sub y over v sub x, you would get dy dx. He goes on to call this equation 3, but I think that equation 3 deserves to have both a contravariant and a covariant form, just like equation 4 does. So this contravariant transformation is the way that displacement vectors transform. But I think that if you're dealing with vector fields instead of displacement vectors, they will transform in a covariant fashion. That is, you should just replace this dy by dx with dx by dy. Now, in order to confirm or reject this hypothesis, I'm going to have to come up with an example of a vector field in one coordinate system and transform it into another coordinate system and see if the result makes more sense using the contravariant or covariant transformation. But that's going to take some time that I just don't have this morning, so we'll leave it at that for now.